A lot of those tend to be more individual work. Here, because I wasn't sure whether people's laptops would have different capabilities, and also because pair programming is fun, I wanted to work in groups. So if you haven't already, if you can cluster yourselves into groups of 4 or 3 if you can't find 4, and to avoid the pain of library installation hell, I wanted to just use Python Anywhere. Unless someone in your group already has numerical Python, scientific Python, matplotlib installed, it's just going to be way easier to run it from that. So do we have any groups that are completely set up right now in terms of you have a group of 4 and someone has a Python Anywhere account? Okay, cool. Yes?
You asked us to raise our hand if we had a Python Anywhere account.
Okay. Yeah. So people who already have a Python Anywhere account, whether you created that in the last 10 minutes or the past 10 years, can you raise your hand? Okay. People who do not have an account, try to form a group with someone who does. So there might only be 1 or 2 groups where someone needs to make one, but it takes about 2 minutes. This will all make sense in a minute. Okay, that's the wrong. Let's do that. Yes, I'll do it.
Just before you start, you just give us a signal so we know.
Okay. Okay. Let's rock and roll. So I know people haven't gotten their teams and their setup quite yet, but I'd like to go real quickly through a bit of an introduction as to what exactly we're going to do for the next couple of hours. So this is our agenda for today. Right now we're doing the introduction, which will include trigonometry on one slide and signal processing on one slide. We're going to play with some Fourier transforms and some spectrograms, and you'll learn what those things are. We'll have some exploration time, and then I think it's going to be about halfway through, and we'll take a 20-minute break. We'll go into sampling and aliasing and all sorts of bad things you can do to signals, noise and filtering. And if we have extra time, I'm not sure how far we're going to get here, we'll play with formats, spell coding, frequency shifting, and more advanced type fun topic. And at the end, I want to come back because one of the things this talk is it's basically impossible to teach signal processing in 3 hours. But what I'm trying to do by illustration is, well, see, this is usually an upper level class that has ridiculous numbers of prerequisites and costs a lot because MATLAB is expensive. And so I'm assuming, in the workshop description you saw that I think people will walk in here knowing how to code in Python and algebra. Note that I'm not assuming trigonometry background. I'm not assuming that you took differential equations. We will not see random crazy math squiggle things on this board. We're not going to get that today. But because of that, we're going to be skipping a whole lot of things. You will not walk out of here with the equivalent of that 3-credit class. And so these are some of the things that we are skipping. Right? We're not going to see the math. We're not going to work with images. There's a lot of signal processing in a lot of different fields. There's image transformations, there's audio transformations, there's like weird things that people use to find the outlines of buildings and with heat maps in the dark. We're not doing that. But we will be playing with audio. We're going to be taking some of the basic concepts in a fundamental signal processing class and trying to get a gut feel from them. And the way we're going to do this is in team, because I'm guessing there's a range of Python experience levels in this room, there's a range of programming backgrounds in this room, there's a range of math backgrounds in this room, and there may be a range of signal processing exposure in this room. So just a quick show of hands, has anybody here actually taken any signal processing classes before? Okay, so maybe a third of the room. So you folks are probably going to find some of these things really elementary, but the presentation might be a little different from what you're used to in those classes. The side note is, the genesis of this tutorial was that I'm a grad student, I'm a PhD student at Purdue in the engineering department, and I was asked to teach the signal processing class to graduate students in audiology who are training to become clinical audiologists, basically doctors. And they don't typically have programming background. In fact, the first time I showed them code, they all started getting this like panicked look on their faces. They don't have mathematical background. They mostly want to work with patients, but they need to understand what some of the things going on in the technology are. And that's where some of these things came from, and going, okay, the math lab is scaring them, the math is scaring them, what can we do to give them just a better feel for it? And that's why I'm not quite sure what we're going to be getting through today. So with the group formation thing, I want to get that in order. How many people are in a group right now? How many people know their team? Okay. Does anybody not know what team they are on? Okay. Can you bump forward to the row in front of you and join? Are you guys in a third row, one group or two groups? Third row. Okay. Okay, two groups. So if you can hop forward and join one of those two teams, that'd be great. Does everybody else have a team? Cool. Does every team have someone with a Python Anywhere account? Okay, does any team not have someone with a Python Anywhere account?
Is it possible that a team has more than one Python Anywhere?
That is fine. If you have more than one, that is perfectly fine. Okay, like I said, the setup is going to be a little weird because we're going to do a whole lot of things simultaneously here. Yes? That would be fine too. Okay. Wait. So what is going to happen? A few things are going to start happening simultaneously, and the next 10 minutes or so will be utter chaos. Thing that is happening, number one, this piece of paper is going to start circulating across the room, beginning with Sam. And if I can have email addresses, at least one person from each team can write down the email account associated with the Python Anywhere account or the Python Anywhere account name so that I can share the screen that's projected. You'll be able to see it, you'll be able to type it in your own terminals, but so you also don't have to type it in your own terminals. So that sheet is going to circulate around collecting usernames and emails. The second thing that's going to happen is that I will start introducing trigonometry and signal processing here in just a moment. And the third thing that's going to happen, if I can find the slide it's on. Aha. Okay. The third thing that's going to happen is after that sheet is passing around, I'm getting people hooked up with the terminal on the screen, is we're going to start writing with and playing with some code. And so the other link that most people are going to want to pull up in their laptop is this one, better.primarypad.com/p/pycon.sigproc. That is going to be an ether pad instance, basically a giant shared notepad. And throughout the next 3 hours, we're going to be playing in the terminal together. We're going to be doing most things in the terminal. But when we come up with little snippets of code that are useful and we may want to use repeatedly, we're going to put them in there. I'll show you what it looks like right now. It looks woefully empty right now, basically. But whenever, and anyone can come in and edit this anytime. If there's a snippet of code you find useful, put it in here. Comment everything that isn't Python code, please, and 4 spaces for a tab. And at the end of the session, we'll have everything that's automatically going to be licensed under DPR 3.0. And at the end of the session, we'll have a bunch of hopefully useful little snippets that people can use as you're remixing little projects in your group. So you can tell already this is based on a lab-style classroom, which is why the setup is a little bit funky. So, does anybody need this link for a bit longer? Okay, one. Let me know when you're good. Are you folks in here for the DSP tutorial? People are trickling in from the back? This is one. This is room number 1. Okay. And I may not notice if new people wander in. If anyone notices new people wandering in, lasso them and bring them to a team. All right? Cool. So, water sheet is circulating. This is all you need to know about trigonometry for the purposes of the tutorial. And some of these things are, did everybody get a little definitions worksheet when you came in? Okay. Are there any extras just in case more people walk in? I'm not sure what a stack of papers meant. We'll worry about that when it happens. So trigonometry on one side. This is a sine wave. So called because it is a wave. It is generated a function called sine. Predictably in Python, the function you call it is called sine. We'll do that in just a moment. But there are a couple of things, a couple of words that we're going to use here. You see the little lambda? That's the wavelength. So the wavelength is the length of a wave. Not a huge deal. The amplitude is the height of the wave. And if you think about this just in sound terms, the higher the amplitude, the louder the sound is. And then the longer the wavelength, the lower the sound is. So there's also, so that the little definition sheet has empty spaces on purpose so that you can scribble in whatever definitions make the most sense to you. So wave, amplitude is height / volume. Wavelength is the length of the wave. The inverse of the wavelength, 1 divided by the wavelength, is the frequency. And so you can see if you have a really, really big wave, a long wavelength, 1 divided by that becomes a very small number. If you have a very short wavelength, that becomes a high number. That's where we got low frequencies and high frequencies from. That is all you need to know about trigonometry. I'm not sure why they make that a prerequisite class. And now that we know trig, this is sampling in one slide. So you might have noticed that in the tutorial description, we talked about digital signal processing. And it's digital because we're doing it with computers. Now, sound waves and most signals in nature, in the real world, are continuous. That means they have infinite resolution, they're all smooth and everything. But to get them into our computer, so we can work with them in numbers, we have to do something called sampling, where we take them from a continuous signal into being a discrete signal. And the sampling frequency is how frequently we sample a signal. So this one, just the little blue lines are just showing these are the points I'm capturing, and so you end up with a kind of jaggedy signal. The higher sampling frequency, the more little blue points you have, and the higher resolution your digital signal is going to be. The lower sampling frequency, the less resolution you're going to have, and probably the worse it's going to sound. And those two slides are all the math and signal processing background you're going to need for the next couple of hours, literally. So, not talking good. Now let's write some Python. Let me get this window on screen. Where is the sheet of email addresses? Is it still passing around? Okay. Whenever the last person has it, just run it up here and I'll get things in. For the time being, you're unfortunately going to have to look at my screen for a little bit. It's okay? I'm going to be doing the questionable thing of like trying to type while looking. Okay. Yeah. So the first thing we need to do is import the libraries. So one of the things we're doing and treating in a lot of signal processing classes in engineering school, you have to write all of these functions from scratch. I don't care about you writing them from scratch. You usually write them from scratch because you have a zone out of math. But we want to actually create what they are. So we're just going to import numerical Python, which has all sorts of useful things, including sine. So let's generate a sine wave. So that just generates an array of numbers. And then we're going to make a signal. Signal equals sine of 2 times pi times, let's make this a 1250 hertz signal. Okay, so what I have just done, and you can treat as much of this as black magic as you like. We've generated a signal, that is a sine wave, and the 2 pi is magic that you need to do to make the sine wave get to the right scale. And we decided to make it 1250 hertz signal, 1250 hertz signal, and sample at 1,000 hertz. And 1 hertz is 1,000 samples per second, 1,000 cycles per second. That's just a unit of measurement. So that might sound a little weird, but let's take a look at what that looks like. So import. Okay. Oops. There you go. I forgot to clear it before I save it last time. Okay, so that is our signal. There you go. And so you can see it's a single wave moving up and down and up and down. And is the sheet passed around? Okay. So, cool. To the third. This one? Okay. So, I'll also put this in the Etherpad. But nah. Okay, and the code I just ran is also in Etherpad, so people don't want to do copy pasting. This arrangement does work better once you start working in your groups. So you have a sine signal. Okay. So the next thing we're going to do is to take the Fourier transform of the signal. And what this does is, right now we have one signal just going along, and it's a single frequency, it's a single beep. So if you were going to graph that in time, it would look like that, it's a wave. And if you were going to graph that in a frequency spectrum, it would look like nothing, 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 1250, nothing, 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 nothing. And the Fourier transform is the name of the magical black box function that takes things from the time domain to the frequency domain. And here we have in the numerical Python library, there's a bunch of functions in the FFT group. And there's one called the real fast Fourier transform, and that's what we're running through right now. And I have treated and made a function that will plot instead of having to call pyplot dot blah 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 all the time. It is in Etherpad. I'm just going to call it now. So make graph data. See what that looks like. So that looks different. Oh. There. This looks different because this is the frequency spectrum instead of a time spectrum. And what this is telling us, and we're going to clean it up in a little bit successively, what this is telling us is, generally speaking, there's not a whole lot here, but there's one note. And that is, in fact, the note that we put in. The reason why it's really jaggedy is if you remember sampling, we have a certain sample rate. We only generated 256 data points. If we go back here like this, we only have 256 data points. And so that wave looked nice and smooth when it was up there, but it's actually made of lots of little tiny bits of jaggedy pieces. And so when the functions tried to figure out what frequencies they were, they got it almost right, but not quite right. And also note that we had 256 data points, but we're actually only seeing 127 of them on the graph. And that is, again, I'm going to kind of wave my hands and say, when you take real valued Fourier transforms, half of your data points go away. Because if it tried to graph all of them, it would basically be this graph flipped over. It would be symmetrical. And so it's redundant information we don't calculate. And so just kind of remember that as half the data goes away. This is what you end up calculating for the frequencies. So this is a really, really messy graph. We're going to clean it up a little bit. So right now we have all sorts of random positive and negative numbers. And so, and also, if you take a look like what kind of numbers are in the data, we'll see that they're complex numbers. So complex numbers, you might notice, were also not in the required introduction thing. So you can also think of them as magical math you don't need to remember. But for those who want to know, or for those who already do, complex numbers have imaginary parts. The j stands for the square root of -1. But when we plot it, only the real component, and so each of these numbers has two parts, a thing without j and a thing with j. And right now, we're only plotting the thing without j. And that's part of why it looks really jaggedy. So the j parts are invisible, but if we want to see what it actually looks like with both the real and imaginary parts together, we can just take the absolute value get the magnitude, and that looks much cleaner. So now we very clearly have, wow, we had one frequency in there. The other thing is that we usually don't, right now this is a straight up graph, we usually don't represent sound in terms of absolute magnitudes, we usually represent sound in terms of decibels. And a decibel, the math for it is 10 log 10 sound. So if we convert that to the decibel scale, and we plot it, we found out that it's about 50 decibels, which is medium-ish loud. And the rest of it is very, very quiet. So on what? I want to get people playing with their computers as soon as possible. So I want to put these in so people can start showing terminals. But what I'd like folks to do while I'm doing that is, in your team, see if you can play around with just generating some sine waves and see if you can play around with adding multiple sine waves. So right now we have one peak showing up. See if you can generate a couple of sine waves and plot them like this so that you see multiple spikes. So if you add two notes, you should see two spikes and they should be a certain distance apart. And the bonus question we're going to try to figure out here is, what is the relationship between the frequency of the sine waves you're generating and the tick marks on the bottom of your screen? So note that we generated a 1250 hertz sine wave, but this index is maybe somewhere around 24. So what's the relationship between the frequency you generate and the spike it puts up? So group fun time, go. Yeah. Let me put the that was on. There we go. I'm going to put the code snippets in the Etherpad also so you can play with it, and then I'll get everyone added. Okay, everything is in the Etherpad now, and I'm going to get everyone added to the main terminal so you can play that a bit more easily. a way to make that fold up. So I was checking on how many groups have generated a sinusoid. Okay, a couple. How many groups have generated 2 sinusoids? Okay. How many groups are still working on their first sinusoid? Okay. I'm going to walk around and check in with the groups that haven't gotten sinusoids going yet, and the ones who have, keep trying to figure out what the relationship is. And when you get it, wave. Okay, so you can keep working if you want, but I'm going to start going through what we were trying to figure out here. So feel free to either pay attention to me working through that or to keep on working through it yourself. So we were trying to have the answer. So I think people should have the Python Anywhere console access invite in their email by now, hopefully. And if anybody knows how to make this part go away so you can see more terminal, let me know. So in terms of generating a signal that has more than one sinusoid in it, you just add them together. And some of you, I think, have seen that, and it's also in the little pasted code in Etherpad. So, and what that graph looks like is like this. So you can see there's two sinusoids that are added together, so it's a little bit more complex of a wave shape. You've got one that's sort of hooking into the other. And taking the Fourier transform of that one ends up looking like this. So instead of one spike, we now have two spikes, which is good because we have two tones in there. And if we take the magnitude of that and we normalize it to decibels and we plot that, it looks like this. So does that graph seem logical? So if we go back a little bit, we'll see that the two frequencies that they chose were 1250 and 625. One is twice the other. And so from this graph standpoint, that kind of makes sense because you get one wave, but twice as juts out at the other. So you have the really, really high amplitude waves where both of them are doubling up, and then the less high amplitude waves where it's only the higher frequency one there. Right? And then when we go to our graph in this frequency domain, you can see that this is twice that peak, right? The rightmost peak is twice the leftmost peak. They're evenly spaced. And so in terms of, well, if we were just given this graph and told, so what frequencies does those correspond to? That goes back to some of the sampling rate stuff that we did earlier. So, let's scroll down. Math. Okay. So by default, the FFT function in MirklePython goes from 0 to 5,000 hertz window, which is relatively reasonable. That's most of, when we think about like human speeds and noise like that, that's a decent window for it. So the x-axis here is, it goes from 0 to 128. Remember, you had 128 elements in the array. And so that's 5,000 hertz. This entire thing is 5,000 hertz. And so each of the little elements here, each data point, corresponds to 5,000 divided by 128 hertz windows, which is approximately 5,000 divided by 39 hertz or so. And so each of the data points in this graph and each of the little tiny segments in here is about a 40 hertz window-ish. And the peaks are not quite 20, so maybe 15 or 16, and then maybe 30 or so-ish. So like 15 and 30. And if we actually looked at the data for the FFT, which you can do on your computers, you'd find it was actually 16 and 32 in the index of the array. So about 40 times 16 is 540, which is pretty close. There's 640, and 40 times 32. So 640 and 1280, which is not too bad considering that our original frequencies were 1250. We got 1280, pretty close. and 625, so 640 is pretty close. So that's how you match up the graph of this with the frequency you entered. Huh? Why 40?
Yes.
Why 40 what?
You multiply by 40.
Oh, yeah, because the FFT library, the numerical PyCon FFT function, takes from 0 to 5,000 hertz. It finds the frequency spectrum. So what that means is if you generate a sinusoid, and you can try this, if you generate a sinusoid that's like 100,000 hertz, and you try to put it through the Fourier transform and try to find a frequency spectrum, it will start doing really strange things because it's outside the window it can handle. And so, and the reason that I put 40 is because it takes a 5,000 hertz window. This is the frequency spectrum. It says nothing, note, nothing, higher note. Because this is 5,000 hertz, and there's 128 data points in there. Each data point in our array is equal to 5,000 divided by 128 little window bandwidth. If we had more data points, it would be a smoother graph. So what I wanted to show you next is, now that we have a slightly more complex signal, and we'll get to happy fun play in a moment. Now that we have a more complex signal with two sinusoids added together, there's a visualization that can help us with more complex things. So this shows the signal in time. This shows the signal in frequency. What if we could see both of them at the same time? What if we had something that had signals whose frequency changed with time? So for that, there's a visualization called a spectrogram, which you can think of as colorful sheet music. And so on the bottom is the spectrogram. So on the top, you can see like sheet music is basically, you can see the frequency and the time. So as time goes that way, frequencies are arranged up and down. And so spectrogram is essentially time goes this way, horizontally frequency goes up, and then color indicates the intensity. And if we wanted to plot that, PyLab has a spectrogram function. Now if you clear the screen here, you can input just the raw signal into it. And that is the spectrogram of the signal. So because we have two constant sinusoids, it looks really boring when it's moving horizontally. You can see it's basically this graph. If we took it and extruded it out and then looked at it from the top, that's what the spectrogram would look like. So that was the boring part. Sinusoids are kind of boring. Now this is for just by show of hands, how many people have the capability to record wave files on their laptop? Or think they might? A couple. Okay, we're going to be doing that. And groups will be moving and passing around. And for those who don't, I have a wave file in here that people can play with, and we can pass those around to the group that don't have recording capabilities. So what I'm going to do is I'm going to put the spectrogram code snip into an Etherpad. That's zoom out for me. And then I'm going to put more code into Etherpad. So you have what I'm about to walk through instead of having to wait for me to finish. So what I'm going to do now is to show people how to read in wave files, get the data from them, and then we can start playing with and filtering and seeing spectrograms of more complex things. And so since you all have the code in Etherpad now, feel free to stop paying attention to me and messing around with that instead at any given point in time. There we go. Okay. So there's two ways to work with wave files in Python. Well, two ways I know of that don't drive me nuts. One is the scientific Python library, which is what we're going to use here, and the other one is there's a native wave library in Python, and if people want to see how to use that, I can show it during the break, and you immediately see why we're not using that library here. So this is the sound we're working with. It's a little more interesting than sine wave. It's a flute playing a single note. It's not that much more interesting than a sine wave. But when you start recording things you can sing, it'll be a lot more entertaining. So I'm going to just define a function. And this is all in the Etherpad code. So what this looks like is just walking through this a little bit. Take a look at the SciPy IO. This is what's going on step by step through that little function. So we call the read wave function on the flute sound. Come on. Wave out. Wave file. I can type. There we go. There we go. And we take a look at what that looks like. We see a bunch of numbers. So if you look up at the documentation for that function, you'll see it returns a couple of things. One, the first thing it returns is the sample rate. So if you remember, the sample rate is how frequently, how many times per second we're going to sample the sine. And 44,100 is the default sampling rate for CD, so that's CD quality sound. And then the next thing it returns is the giant array of numbers. So that's sort of the same thing as the sinusoidal generated. That's the raw sound data file. And it happens to have sort of in this data type to save room. Not really important. So, since we only really care about the data, that's what the little wrapper function is for, so we only get the data. So now, we just have the array. And so now we've just seen reading from a wave file. I'm going to show you writing to a wave file. And now that you know how to do some things with it in between, we're going to learn increasingly interesting things to do in between. So that's reading from, and then writing to. Just a call to. So you can see that these cards are really simple. The name of the file you want to output it to, the sample rate, which in this case was 44100, and then the array of data. So flute again. We can test that. And it's identical to the output since we haven't done anything to it. And so now you know how to read wave files and output wave files. Come again? The wave file? Oh, we can get the wave file. Yeah, so this is where I wanted people to start recording their own sounds when we had happy group time. I also put a thumb drive up here that has the flute sound on it. And so if at any point in time you want to come up and grab it and use that flute, you can. Yes. Thank you, Sam. Yeah, so if you go to the temperature link, the wave file is also there for downloading. So. I'll put that at the bottom of the pad also. So the wave file download link is now at the bottom of the Etherpad on line 171. And so what I'm going to do now is I'm going to generate the frequency spectrum and the spectrogram for the flute sound. And you have a choice. You can either follow along with me playing with the flute sound, or you can grab wave files from your own computer and do the stuff with sounds that you either have or find or record yourself. That's a lot of samples. Okay. I'm just going to keep going through here, and people can keep playing with the sound files if they want. And so I'm looking for the frequency spectrum of the flute sound. And I did the same thing. Took the FFT and I graphed it. And the graph looks like, blah. There's a sound, blah. And if we do the same thing we did before with normalizing the decibels by taking the magnitude and then converting to decibels. We got something that looked like this. So you can see like the flute, the frequency of the flute is a lot more complicated than the frequency of a single tone. And in particular, the flute has the little jaggedy lines here. The bass note the flute is trying to play is somewhere around here, and then these are things called harmonics. And harmonics are multiples of the core frequency that the note is trying to go, and different harmonics are what make different things sound, different instruments playing the same note sound different. And let me, there's actually probably a good, I just skip through. For instance, these are 3 different vowels in a spectrogram, and they're all saying the same bass frequency. Cool, what was that? But because of the different combinations of frequencies around that bass frequency, that's what makes the ah and e sound different. That's skipping way ahead. Okay. And if we make a spectrogram, okay. So it went up to 5,000 hertz, you mean? This one? That's the entire audio, so the frequency spectrum compresses all the time together. Does, I wasn't sure if I didn't hear the question.
I was just making a comment that you were saying that this encompasses the entire 1 second audio file, but
yeah.
It's really half the number of samples. You did the FFT earlier, where you removed half your data.
Oh, it's taking the frequencies of the entire 1 second of flute playing, but the flute playing data had 60,000 something data points, and the Fourier transform, like in the frequency space, only has 30,000 something. So it's taking the frequencies from the entire length of time of the flute. It's not stopping halfway through the flute sound, but the number of data points it returns is half of the number of data points of the time signal. So your frequency signal has less resolution than your time signal. Spectrogram. Audio. There we go. So that's the spectrogram of our flute sound. And if you compare it, if you remember what the spectrogram of just the sinusoid looked like, it looked like nothing except a single bar across. And here we see really dark red at the bottom, sort of slightly darker red here, and then stripes. And the stripes seem like they're pretty evenly spaced. So this one, you can see like the flute started blowing a little harder over time, so it went and these are the harmonics that make it sound like a flute instead of like a guitar or like a piano or something. So, okay. So now you have the code for inputting wave files and outputting wave files. I want people to try making a wave file of the pure sinusoids that are generated. You may need more than 256 samples to get more than 0.1 seconds of data. And the flute that we heard was, the note it was playing was a B, which is about 494 hertz. see if you can generate a single sinusoid of that and compare it to the sine of the flute, which is on the thumb drive up there. And if you really want, if you've got through all that and you want to have more fun, try taking the flute sample and the sinusoid signal, putting them together and seeing what happens with a spectrogram of that, what that looks like. So I'm going to start wandering around again, but it's like team group lab time. Maybe not if you have questions. All right, so people are finding, some groups are finding some really, really interesting things. I wanted to point out three things. The third thing I wanted to point out is that it is 10:30 and it is technically break time. Since we're sort of in free play time anyway, I'm just going to say that's going to go on for at least 20 more minutes, and you're welcome to drift in and do whatever you want. Two interesting things people have been finding. One is that they generate a sine wave and it doesn't play, it doesn't do anything. And these are like things that I was hoping people would discover through the course of playing with us. That's why we have a little lab. One is that the sine function generates really tiny amplitudes. All the values are between -1 and 1. And if you compare that to the data you get when you read in the flute wave file, you'll find that those numbers are gigantic. They're like 20,000, 17,000. And so increasing the amplitude of your signal might give you an audible thing. The second thing, which we'll get into after the break, is when you get an audible wave file, sometimes it doesn't sound like a pure tone. And so if you're running across that, try playing with different variables, try changing the sampling rate, try changing the frequency, and see if you can come up with any ideas why that might be the case. So with that, I'm gonna keep kind of circling around, and we are officially in 20-minute break/free play time, which is also a good opportunity to record wave files. And if you end up recording sounds that you want to share with people, the thumb drive here will be sort of a communal Dropbox thing. know how to, so does anybody in the room know how to work with different SciPy versions?
Or to upgrade, because I'm having trouble upgrading my SciPy. I'm getting like... So no, so because we have an old version of SciPy, so I tried upgrading it, but I'm getting like compiler errors. What did you do?
So people have been playing around with various things, and I've seen some really, really interesting stuff. So I wanted to do, coming back from break, I wanted to do a bit of show and tell and fun things people have found. And you folks want to?
Oh, sure.
I've got the slide up. So these fellows actually inadvertently found a preview to one of the next things I wanted to talk about. So that would probably make a bit good lead-in.
Hello, there we go. All right, so we got through the sample, and we decided to, well, so when we looked at the graph, where's my cursor? Here we go. All right, so when we looked at the graph, can I slide this over here? All right, we noticed some interesting things. I don't know, here, let me point at it. I don't know if you can tell, but there's sort of like these spots here that are a lighter color than the other ones. We thought that's interesting. And then we thought about it a little bit more, and some of us have a little bit more experience maybe. And in music, I don't know if any of you play an instrument, but when you're trying to tune the instrument, you tend to listen for what's called beating. And that's when if you're tuning against somebody else that's playing the proper pitch, right? So what happens is when you get two sine waves that are close in frequency, you'll start to get interference, what's called interference. So that's when the troughs and the peaks line up that would cancel out the sound, right? So what we found, we thought, okay, well, this kind of looks like what's happening. These kind of look like this beating, this pulsing, right? And so what we decided to do is we know a little bit about how you construct the sine wave functions, and we decided that we were going to try and do what's called phase shifting. What that means is basically when you have a sine wave, the phase is where relative to a 0 point, like the peak of the wave is. You can sort of think of it that way. So we basically you shift the waves slightly. We used pi because we know that's one, what is that, quarter of a cycle. And what ended up happening is I don't know if you can, these are lined up well enough, but when they're lined up well enough, you can actually see that these sort of beating or these will shift slightly and be equivalent all across the board. And what that indicates actually is that this person there you go. This person that's playing this flute note is actually not playing the constant frequency. And so that's why it's kind of, here you can kind of see it's longer. That indicates they're closer to the pitch. No, yes. They're closer to the pitch, and as they go along, they get further away from the proper pitch. So there's just something interesting, so we made a couple of graphs to investigate that. Exactly. It's pretty good.
You want to, maybe you can play the sound for them as well?
Sure, yeah. So this is the original sound. Okay, and then, oh, oops. Almost there. Hear that? That's the beating that we're talking about. The interference lines up so that it kind of either gets too loud or too soft. And actually, that's probably clipping. Yeah. That's why it sounds funny. It's clipping a little bit because it's over the. It's too great a volume, basically. Cool. That's what we found.
Okay. And I think this is going to start turning, okay, microphone is on. So that brings me to a couple of things I wanted to introduce in the second half, and then we'll kind of go around and keep playing, because this usually happens when you do this sort of thing, is that people find way more interesting things that I had actually planned on teaching. So I'll show you some of the things I have here, and then we'll go off on more interesting tangents as we pull in, and we'll go like, oh, that was really cool, and come back. Okay. So we're still sort of in the middle of playtime. This is one of the reasons why I was like, I'm not sure if we're going to get the vocoding at the end. So one of the things they found is starting to lead towards the importance of sampling. So as you specified the writing of your wave files, you had to tell it what sampling rate. Was it 10,000? Was it 441? 100? Was it whatever it was? And if you remember from earlier, that the reason why that's important is because the waveforms are in time, and so making sure that when you digitize them and then play them back, the digital versions are spaced in the same format. When we digitize wave files, and then we output them again as audio, the audio is continuous again. And so when we go from continuous to discrete back to continuous, we need to make sure that we're not, well, we need to try really hard to not distort the sound whenever possible. And so by making sure we have the same sampling frequency, imagine if only every other point was represented, or if we thought, oh, when we output it as a sound file again, all those blue points are twice as close as they actually are. You'd end up with a much higher frequency signal because the waveform would be smushed in time. And so the sample rate that you both sample the sound at and then tell the sound to play back at matters a whole lot when you're doing audio processing and when you're doing other kinds of processing as well. And the visual equivalent would be image resolution. Generally speaking, higher sample rates are better, but there's a trade-off that it's more data, it's more stuff to compute, it's going to take your computer a longer time to crunch it. So, sampling again. And specifically, one of the things that can happen when you undersample, which means you don't take enough samples to reconstruct a signal accurately, is aliasing, which is that when you play the signal back, it sounds like a lower tone than it actually is because you've undersampled. So this is a picture of aliasing, and the red waveform is the original sound, it's the original tone. But you can see how if you only sample at the point where the black dots are, and then you only had those points, and you were thinking, geez, what was the original waveform? You would draw the blue line, and you would end up with something that's a lower frequency signal. So it gets aliased as that. And the long definition term for it is the Nyquist-Shannon sampling theorem, which has that definition. So I changed it into haiku. Basically speaking, so way back to the beginning, at 9:15 this morning, we started generating sinusoids, and those sinusoids had a particular frequency. So for a sound, so let's say you generated something that was 500 hertz. You would need to sample that at least 1,000 hertz in order to be able to accurately represent it. So your sample rate always has to be at least twice the highest frequency present. And so one of the things I wanted to have people play with is, now that you know that the sampling stuff actually does matter quite a bit, is playing with that. What happens if you have your sinusoid and you generate it at a particular sample rate, but you turn that into a wave file that has a higher or lower sample rate? What if, even if you just have the flute wave file in and out, what would happen if you trimmed the output sampling rate? I can play with that up here a little bit if people would like, but I thought I'd throw this out here as information you can play with, and it seems like people were in the middle of some really interesting explorations, so I'm going to run around and see what's happening, and then come back up here, show you flutes, and see what else has popped up. Anybody else have anything? Nothing? Okay. So now you have extra sampling stuff to play with, and keep doing whatever you find most interesting.
Yeah. Cool. Fine. No, it's fine. I can. Yeah. Hello, everyone. Sorry to disturb you while you're hacking around. I came along to this talk just to see everything that was going on, just to sort of put some perspective on stuff you can do with audio analysis. I'm a pharmacologist, and I work in London in the UK, and I do audio analysis of sounds that you get out of the lung to see whether you can classify disease states from them. There's a couple of tools that I use frequently, which I think is going to be a lot of fun for you guys when you're hacking around, because A, they're open source, and B, they're really, really quite good. So one of the things I wanted to bring your attention to, do I just spin onto the other? There we are. Fine. Okay. Excuse the fat fingering. Okay, so this is an open source program that's developed by Queen Mary's University in London, which I've been also part of the development of. It's fantastic for analyzing audio signals. Python's fantastic for doing all the batch and scripting analysis of what you plan to do with your audio signals. But if you want to look at your wave signals, look at your spectrograms, look at your average spectrograms, spectrograms over time, then this stuff's fantastic. It also has a huge library of analytical protocols if you are planning to do things like, I guess the main thing these things develop for is for music. So if you want to do beat matching, and you want to match two sound, if you had two audio tracks, they want to match the tempo so they were the same, so you could mix them if you were a DJ, for instance. And that's some of the stuff you can do with this. Yeah, if you go ahead and download it, it works on all platforms. And it's really solid. It has, in particular, an annotation layer that's written in XML. So what you can do is you can have your audio signal, you can annotate various bits of interest from your signal in XML, and that gives you your mapping coordinates, then run that in Python. So that makes it particularly useful for working with both this and in Python. And one of the things I should probably go and open source, I've basically built a package which makes it a lot easier to work with this in Python. So at some point I should probably try and release that. But just to give you an example of one of the things that it does. Where am I? Okay, so this is, for instance, this is a spectrogram of a cough. And unlike the lovely examples that Mel has with the flute, which has these very strong, maybe 10,000 times louder in certain frequency bands for a pure note, like a B or a C or something, I get a lot of garbage out of my animals and humans and things like that. So yeah, just give you an example of noise. So I use a 4.1 recording system now. So I have 4 microphones at different points, and I summate those to get the best strength of the signal. So this particular one is an animal sitting in a sealed box. So it's just a microphone to the side wall of the chamber. But yeah, for a human, you can either have a lapel microphone, like this one I have here. What's even better is to have it fixed against something like your pharynx or your larynx or something like that, or possibly against your chest as well, because you pick up lots of, as sound moves through the air, it of course diffracts and refracts, and you get lots of noise of it just moving through the air. So if you can get stuff where it's attached directly to where the sound's being propagated, you get a stronger signal. So it's a lot easier to get the signal out of the noise. Oh, right, so, yeah, so for instance, if someone has a healthy cough, right, and it's just something like if you, there is no good algorithm for counting cough, which sounds like, well, why the heck would you want to do that? Well, the problem is that research goes really slowly if you have to do everything manually, whereas if you do it all automatically, you can have loads of parallel experiments and run them really fast. I come from a background in doing ECG analysis and EEG analysis and things like that, and for instance, you can get any small device now to do like heart rate. You put it on you and it tells you your heart rate's fantastic. And I want to do the same thing with cough. I want to count it, and what we're also doing is classifying. The next stage that I've got a thing for, which may or may not make sense. Okay, let's turn that round. Nope. There we are. Good. Yeah, so also what I do is here is a bunch of various different spectra, which I've broken down into multiple categories. And essentially, some of the peaks you can see, the one that's weighted at 29%, if someone has an inflammatory disorder, which is also wrecking their epithelia in their lung, they tend to get that pattern. So the beauty is that you can also detect whether someone's being exposed to something like ozone from that. So you also have as well, so you could tell someone who has emphysema. As the disease of emphysema gets worse, the magnitude gets louder and the frequencies tend to shift to a lower bassier note because you're getting a lot more of your basically your alveoli rattling around. So in this case, instead of using audio analysis to detect some audio encoded information in something sentient like someone's voice or in music or something like that, you can work out spatial and physical things out of what it does to the frequency in the audio. So yeah, beyond that, I'm basically building algorithms to count and classify cough and sneezes and various other noises that the body makes. Because there wasn't any good commercial offering. There was no one making stuff, so I just built it. Yeah. Yeah. I wish it was that easy. In my particular case, the frequency bands, there's more commonality between like a sneeze and a cough, right, than there is between everything else. So yes, I look at sneezes. Yes, I look at power. I also do things like independent component analysis and principal component analysis to try and work out what are the strong vectors that correlate with each particular thing. This particular one takes each of the different coughs and compares them to one another, and then arbitrary bins them into categories. And then I have to work back with the metadata I got from the experiment to work out whether that's relevant or not. But yeah, frequency is the main part. With audio, all of the information is basically in the frequency domain. Now granted, I say that, and if you say it in front of very learned people, they go, what about the phase as well? And there are these other components to it as well if you really want to get into it. But frequency is one of the core components. And being able to run the FFT nice and quickly and do lots of correlations between these frequency spectra gives you a lot of what you need.
So the reason that I wanted to help you folks see this is because you've already got the very basics of the tools you need to do stuff like this, right? That's basically the first graph that we generated after the plain sine wave, right? That's the frequency spectrum. And spectrograms, you know that now. So these are some of the cool things you can start playing with. And you can, write if statements like, is there a peak at 440 hertz? If that, yes, is cough, things like that. And we also had some folks wanting to help my sinusoid doesn't sound like a sinusoid. And there's a fix for that.
So we were trying to generate the tone, and when you do it right, it should sound like that. But it didn't sound like that. It sounded more like white noise. It played fine on mine, but Windows Media Player doesn't even like it. The problem was that the scipy.io.wavewrite function wants to be given 16-bit integer data type samples. And so the generator, the output of sine is going to be float values varying between 1 and -1. And you need to map those into the range of 16-bit data type, but you also need to make the type actually be int16. So I think she's loading the code samples, and there's a function that explicitly calls the numpy array function to create a new array, and you explicitly set type, d type equals int16. There it is. Oh yeah, that's.
So yeah, that's something that we saw popping up in a couple of different places, and these folks were the first to figure it out. So, yay for that. And just out of curiosity, how many people ran into that they couldn't get their sine wave to play as the? Okay, so yeah, I saw that like all across the room. So yeah. And I want to let people play a little bit with the sampling and aliasing a bit more, and also check in on how people are doing after that fix gets applied. And after that, I want to come back and start doing filters. And so we might not get through everything, and you might not catch everything that I put up here, because we're all doing, sounds like people are sort of spitting out a lot of their own explorations. But I'm trying to give you a sense of, this is how you play with this stuff, this is how you get started with it, these are the kinds of things you can spin out into doing with it. So I am seeing all sorts of really interesting sounds starting to come from this room. I wanted to throw in yet another thing into the mix. So we have gone into wave files, out of wave files, we're generating sounds, we're adding them together, we're expanding frequencies. That's all really cool. Now we've seen how to go from a time domain signal, which is the sound, into the frequency spectrum. Feel free to keep doing things, and if like beeps and whistles pop up in the background, that's fine. What I want to do is show you first a little bit more of the sampling stuff, but I'm going to show you how to go backwards. So given a frequency spectrum, can we reconstruct the original sound? The answer is yes. But so the code is, again, at the bottom of Etherpad. And so what I want to do here, no, not a new tab. I wanted to move this over. Okay. Where's this go? So if you remember, we were playing around with sample rate stuff, and just to start from a clean slate here, if we're going to play with a flute sound again. So we just read the data into audio, and we're going to just read it right back out. So what that means is that if I put a new tab in here, that's future. This is the original flute sound. You've all heard that a million times by now. And then I put it and it to be identical. Flute again. This should sound exactly the same. Should sound, there we go. So identical sound, and then just for the kicks, if we, I forgot these sounds preloaded, but if we were going to half, roughly, the sampling rate, and then double it, you should notice a relationship between the way these three things sound. So here's 441. Play. Kind of hold that tone in your mind. This is roughly half. So it's dropped an octave. And this is doubled. So doubling a frequency takes a note up an octave, and some of you who are musicians might already know this, but that's sort of the relationship between the frequency and the note you hear. And the other thing I wanted to show was going backwards. So we have already done used the fast Fourier transform. No, not that. So we've all done this, right? We've used RFFT to get the frequency spectrum from the original flute audio. And the graph of that looks, if we convert it into decibels, like that. So we've all seen that. And now what we want to do is to go backwards from it. And this is pretty simple. So in functions, there are inverse fast Fourier transforms, and in this case, it's the inverse real fast Fourier transform. So if you give it your the transform, the frequency spectrum, and you give it the original length of your audio file, It'll take a little while because this is relatively computationally intensive. And then if you put that, add it again. And if you put that out to a bar, see if I can remember which tab it is. You get the original wave bar back. And so, yep. So we're looking at the last 3 lines now. So we had so audio was next would be, that would be a good reason why it sounds identical. Okay. Yeah, so let me think around with that for a moment. But one of the things that you can do with this is you can start doing filters. And so what I got that working now. Okay, that was not the flute. Let me fix that. I probably have the wrong sample. But one of the things you can start doing is, if this is supposedly the frequency spectrum, you can start filtering for certain frequencies. So if you mess around with things while you're in frequency domain and you convert it back to the time domain, you'll see the effects of that in the sound you put out. So if we decided that we were going to cut out everything above this line and basically only take the low frequencies, then we get a low pass filter and we would have a lot of the high harmonics of the flute muted. So that's just some spectrogram, some things that sometimes the filters you can do that are really basic. You can pass high things, you can pass low things, you can band pass things. You can, instead of allowing things in the middle to get through, you can block things in the middle, and that's called band stop. You can take out a specific frequency. So if you have a recording and there's a whistle in the background that comes from a fan, you can find a frequency of fan and take that out. And so I wanted to throw that in a mix, and let me get the inverse going. It's just working this morning. I'll get the inverse going and show you how to do that. But I just wanted to put that idea in that you might be able to now work with your sound files while they're in the frequency domain, and then convert them back and see what happens in the meantime. Yeah. Yeah. We are ignoring it for the purposes of this tutorial. And when you take, so we've been using so the question is, when we convert from the time of the wave function to the frequency domain here, do we lose information about the phase? And we've been using the real version of the Fourier transform, so RFFT, there's also FFT, which isn't this real. I'm not entirely sure, but I think that if you use FFT instead of RFFT, you'll be able to retain that information. But that would be a good thing to play around with and check. And I will figure out that answer. But that is also a something that we were not going to be dealing with today, so I didn't check it. But it might be that the reason that didn't just work is that I needed that. But so let me think around and I will come up with a better answer to your question. So, other questions? So the snippet of code that didn't work is an Etherpad, and I'm going to make it work now. Okay, so yeah, I figured out the inverse bug. It's the same int 16 coercion thing that you have in backbound. So if we, and I fixed the code in Etherpad also. If we have, so audio is the original flute wave data. And if we take the FFT of it, and then the inverse of that. And then we coerce it. And then we make the wave. Then we get the reconstructed signal. Sorry about that. So what this means is if you do things like, so this is the frequency spectrum again. If you say, all right, looking at the spectrogram, I don't want to hear any of these high harmonics. I want to cut them off right here. I want like, everything above this to just be 0. You can take a look at the spectrum and say, oh, I guess maybe after the 2000th data point, I want that to be 0. And you can go to your flute FFT array now and zero out a whole bunch of those numbers that correspond to the frequency you want to take out. So I was pretty much running into the end of time. We didn't get to do vocoders and things. Okay. Let's see if I can. So let's see if this works. Check my list iterations here. For I am in 2000, and then however long the signal is. Yeah.
At least my absolute value doesn't get any smaller.
Yeah. You can also change them and say. So, okay, here's what I'll do. We are in the last couple minutes of time for this particular tutorial, but on the worksheet thing, there's a bit.ly link where all the stuff is going to be posted with more annotations and in order with the things that we've generated in the workshop as well. And so I will probably sit down after dinner tonight, write a low-pass filter so you can also run that through the flute sound. And you can move it around, make that band pass or notch or whatnot. So I'll put that, so make a low pass. And so when the code from today, like in the Etherpad file get posted up with graphs and things of what comes out from different outputs. There'll also be a low-pass filter, which I'll put in tonight, because right now I can only think of manually zeroing out everything after a certain index, which seems woefully inefficient. People who know more Python than me may have better ideas. So there are a couple of things that we didn't get to cover that I wanted to zoom by a bit. One was the idea of formants and the different harmonics. So you saw how in the flute we had a couple of different stripes above it. And if we had a different instrument playing here, which we didn't, if we had different instruments, you'd see the same fundamental frequency, but different weights of the various harmonics above that frequency, which is what makes guitars sound like guitars and pianos sound like pianos and flutes sound like flutes. It's also what makes vowels sound like vowels. So if I say a, e, u, they're the same note, but you can tell what vowel I'm saying. And in the speech world, that each vowel comes with different formats, which are different harmonics on top of the frequency you're trying to sing. So I had a list of the formats for different vowels, and so if you put those in, you can actually, by generating sinusoids, you can make a vocoder, which is basically a robotic voice, and you can have different sort of sounding like vowels output at different frequencies as you shift them up and down. Because the thing is, with the ability to do inverse FFTs, not only can you just zero out and block certain things if they're noise, you can also take certain chunks of the frequency spectrum and shift them to complete other chunks of the frequency spectrum. So you can translate things up and down, you can make them wider, you can shrink them. And so by combining those two and some knowledge about the way vowels work, you can actually generate a robotic voice. And so one of the things I was hoping to get to, but we didn't have time for today, was to actually come up with a script that would sing Ave Maria. It would sound like ah, but you can, with the pieces that we have, you can actually do that. And so I'll get that script up tonight also, so y'all can see that and play with it. It sounds really bad. This is why we don't have very good robotic voices. So that was the vocoding. Yeah?
So the frequencies for these formants, are they a proportion to what?
Oh, no. The frequencies for the formant, those are frequencies for the vowel. These are all the vowels being sort of sung at the same frequency. And yeah, so it's not proportional, it's just, you have to remember it's the scale is logarithmic. So you double the frequency to go up one octave. So you'd have to not just shift them linearly, you'd have to double them. So when I upload the vocoding script tonight, you'll see sort of how that works. But that would give you one version of the vowels, and then you can frequency shift them up and down to get singing at different tones. The other thing that if you're going to do more signal processing is you should look at Bodhi plots, which is just a fancy name for some of the graphs that we've been looking at. We've ignored phase completely during this tutorial, but the magnitude Bodhi plot is basically frequency versus magnitude, and this is a high-pass filter. And so what that would mean is what I was talking about with the flute. If you wanted to only hear the low parts down here and not this stuff, you would just take this and zero out everything to the right of maybe 2,000 or so. Alternatively, you could zero everything to the left of 20,000 or so, and that would be a high-pass filter. And these are just ways of visually representing what filters do. It's basically saying we're going to let high stuff go through, and then we're going to make it softer and softer. And the reason why I put the Bodhi plots and formats in the same thing is because some speech sounds are higher or lower frequency than others. And so this is an audiogram. And so you can see that people who, this basically shows that this is a person that can hear really low frequencies but not really high frequencies. And a lot of the high speech sounds are up here. So vowels are down in that corner on the left. but consonants are up on the right side, like the very high sounds. And so sometimes one technique is that you take high frequency data and shift it down or compress it down to be lower frequencies. Or if you're trying to get signals and they're beyond the wavelength that the human eye can see or the human ear can hear, this is the kind of thing you have to do in bringing them into something we can see and hear. So those are things that we didn't get to today, but I will post the code for them tonight, so you can all play with those things. And I'm hoping that this gave you a bit of an idea of how, well, two things. First, how to play with some signal stuff. So now I think everybody has started generating files and can read and write them and has some idea of how you can play with them and filter them and mangle them in between, and the different kinds of trade-offs that you take with algorithms you might choose or sampling rates you might pick. And the second thing is to try showing that a lot of these things are things that they're very basic introductory concepts, but traditionally in school, before you even get to play with that stuff, you have to go through basically 2 years of engineering college. And we started with none of those prerequisites. I know some of you had a lot more than that, but we didn't start assuming any of those things, and we were still able to play with a fair number of ideas. And so I wanted to show people what was possible and see where folks went with playing with it. And it's been really cool to see what people have done and what they've played with. And that's what I've got, and mostly because we're out of time. I'd be happy to play with people and there's more over lunch or in the afternoon, if just find me rendering on PyCon. Thank you for coming. I can also take from here, but I'll be hacking on this in the afternoon for dinner. Tutorials, a lot of those tend to be more individual work. Here, because I wasn't sure whether people's laptops would have different capabilities, and also because pair programming is fun, I wanted to work in groups. So if you haven't already, if you can cluster yourselves into groups of 4 or 3 if you can't find 4, and to avoid the pain of library installation hell, I wanted to just use Python anywhere, unless someone in your group already has numerical Python, scientific Python, matplotlib installed. It's just going to be way easier to run it from that. So do we have any groups that are completely set up right now in terms of you have a group of 4 and someone has a Python Anywhere account? Okay, cool. Yes?
You asked us to raise our hand if we had a Python Anywhere account.
Okay. Yeah. So people who already have a Python Anywhere account, whether you created that in the last 10 minutes or the past 10 years, can you raise your hand? Okay. People who do not have an account, try to form a group with someone who does. So there might only be 1 or 2 groups where someone needs to make one, but it takes about 2 minutes. This will all make sense in a moment. Okay, that's the wrong. Let's do that. Yes, I do.
Just before you start, you just give us a signal so we know.
Okay. Okay. Let's rock and roll. Alright, so I know people haven't gotten their teams and their setup quite yet, but I'd like to go real quickly through a bit of an introduction as to what exactly we're going to do for the next couple of hours. So this is our agenda for today. Right now we're doing the introduction, which will include trigonometry on one slide and signal processing on one slide. We're going to play with some Fourier transforms and some spectrograms, and you'll learn what those things are. We'll have some exploration time, and then I think it's going to be about halfway through, and we'll take a 20-minute break. The math and signal processing background you're going to need for the next couple of hours, literally. So, yeah, that's good. Now let's write some Python. Let me get this window on screen. Where is the sheet of email addresses? Is it still passing around? Okay. Whenever the last person has it, just run it up here and I'll get things in. For the time being, you're unfortunately going to have to look at my screen for a little bit. It's okay? I'm going to be doing the questionable thing of like trying to type while looking. Okay. Yeah. So the first thing we need to do is import the libraries. So one of the things we're doing and treating in a lot of signal processing classes in engineering school, you have to write all of these functions from scratch. I don't care about you writing them from scratch. You usually write them from scratch because you have a zone out of math. But we want to actually create what they are. So we're just going to import numerical Python, which has all sorts of useful things, including sine. So let's generate a sine wave. So that just generates an array of numbers. And then we're going to make a signal. Signal equals sine of 2 times pi times, let's make this a 1250 hertz signal. Okay, so what I have just done, and you can treat as much of this as black magic as you like. We've generated a signal, that is a sine wave, and the 2 pi is magic that you need to do to make the sine wave get to the right scale. And we decided to make it 1250 hertz signal, 1250 hertz signal, and sample at 1,000 hertz. And 1 hertz is 1,000 samples per second, 1,000 cycles per second. That's just a unit of measurement. So that might sound a little weird, but let's take a look at what that looks like. So import. Okay. We'll go into sampling and aliasing and all sorts of bad things you can do to signals, noise and filtering. And if we have extra time, I'm not sure how far we're going to get here, we'll play with formats, bow coding, frequency shifting, and more advanced type fun topic. And at the end, I want to come back because one of the things this talk is it's basically impossible to teach signal processing in 3 hours. But what I'm trying to do by illustration is, well, See, this is usually an upper level class that has ridiculous numbers of prerequisites and costs a lot because MATLAB is expensive. And so I'm assuming, in the workshop description you saw that I think people will walk in here knowing how to code in Python and algebra. Note that I'm not assuming trigonometry background. I'm not assuming that you took differential equations. We will not see random crazy math squiggle things on this board. We're not going to get that today. But because of that, we're going to be skipping a whole lot of things. You will not walk out of here with the equivalent of that 3-credit class. And so these are some of the things that we are skipping. Right? We're not going to see the math. We're not going to work with images. There's a lot of signal processing in a lot of different fields. There's image transformations, there's audio transformations, there's like weird things that people use to find the outlines of buildings and with heat maps in the dark. We're not doing that. But we will be playing with audio. We're going to be taking some of the basic concepts in a fundamental signal processing class and trying to get a gut feel from them. And the way we're going to do this is in team, because I'm guessing there's a range of Python experience levels in this room, there's a range of programming backgrounds in this room, there's a range of math backgrounds in this room, and there may be a range of signal processing exposure in this room. So just a quick show of hands, has anybody here actually taken any signal processing classes before? Okay, so maybe a third of the room. So you folks are probably going to find some of these things really elementary, but the presentation might be a little different from what you're used to in those classes. The side note is, the genesis of this tutorial was that I'm a grad student, I'm a PhD student at Purdue in the engineering department, and I was asked to teach the signal processing class to graduate students in audiology who are training to become clinical audiologists, basically doctors. And they don't typically have programming background. In fact, the first time I showed them code, they all started getting this like panicked look on their faces. They don't have mathematical background. They mostly want to work with patients, but they need to understand what some of the things going on in the technology are. And that's where some of these things came from, and going, okay, the MATLAB is scaring them, the math is scaring them, what can we do to give them just a better feel for it? And that's why I'm not quite sure what we're going to be getting through today. So with the group formation thing, I want to get that in order. How many people are in a group right now? How many people know their team? Okay. Does anybody not know what team they are on? Okay. Can you bump forward to the row in front of you and join? Are you guys in a third row, one group or two groups? Third row. Okay. Okay, two groups. So if you can hop forward and join one of those two teams, that'd be great. Does everybody else have a team? Cool. Does every team have someone with a Python Anywhere account? Okay. Does any team not have someone with a Python Anywhere account?
Is it possible that a team has more than one Python Anywhere account?
That is fine. If you have more than one, that is perfectly fine. Okay. Like I said, the setup is going to be a little weird because we're going to do a whole lot of things simultaneously here. Yes? That would be fine too. Okay. Wait. So what is going to happen? A few things are going to start happening simultaneously, and the next 10 minutes or so will be utter chaos. Thing that is happening, number one, this piece of paper is going to start circulating across the room, beginning with Sam. And if I can have email addresses, at least one person from each team can write down the email account associated with the Python Anywhere account or the Python Anywhere account name so that I can share the screen that's projected. You'll be able to see it, you'll be able to type it in your own terminals, but so you also don't have to type it in your own terminals. So that sheet is going to circulate around collecting usernames and emails. The second thing that's going to happen is that I will start introducing trigonometry and signal processing here in just a moment. And the third thing that's going to happen, if I can find the slide it's on, Aha. Okay. The third thing that's going to happen is after that sheet is passing around, I'm getting people hooked up with the terminal on the screen, is we're going to start writing with and playing with some code. And so the other link that most people are going to want to pull up in their laptop is this one, better.primarypad.com/p/pycon.sigproc. That is going to be an Etherpad instance, basically a giant shared notepad. And throughout the next 3 hours, we're going to be playing in the terminal together. We're going to be doing most things in the terminal. But when we come up with little snippets of code that are useful and we may want to use repeatedly, we're going to put them in there. I'll show you what it looks like right now. It looks woefully empty right now, basically. But whenever, and anyone can come in and edit this anytime. If there's a snippet of code you find useful, put it in here. Comment everything that isn't Python code, please, and 4 spaces for a tab. And at the end of the session, we'll have everything that's automatically going to be licensed under DPL 3.0. And at the end of the session, we'll have a bunch of hopefully useful little snippets that people can use as you're remixing little projects in your group. So you can tell already this is based on a lab-style classroom, which is why the setup is a little bit funky. So, does anybody need this link for a bit longer? Okay, run. Let me know when you're good. Are you folks in here for the DSP tutorial? People are trickling in from the back? This is one. This is room number 1. Okay. And I may not notice if new people wander in. If anyone notices new people wandering in, lasso them and bring them to a team. All right? Cool. So, while the sheet is circulating, this is all you need to know about trigonometry for the purposes of the tutorial. And some of these things are, did everybody get a little definitions worksheet when you came in? Okay. Are there any extras just in case more people walk in? I'm not sure what a stack of papers meant. We'll worry about that when it happens. So trigonometry on one side. This is a sine wave. So called because it is a wave. It is generated a function called sine. Predictably in Python, you call it, the function you call it is called sine. We'll do that in just a moment. But there are a couple of things, a couple of words that we're going to use here. You see the little lambda? That's the wavelength. So the wavelength is the length of a wave. Not a huge deal. The amplitude is the height of the wave. And if you think about this just in sound terms, the higher the amplitude, the louder the sound is. And then the longer the wavelength, the lower the sound is. So there's also, so that the little definition sheet has empty spaces on purpose so that you can scribble in whatever definitions make the most sense to you. So wave, amplitude is height / volume. Wavelength is the length of the wave. The inverse of the wavelength, 1 divided by the wavelength, is the frequency. And so you can see if you have a really, really big wave, a long wavelength, 1 divided by that becomes a very small number. If you have a very short wavelength, that becomes a high number. That's where we got low frequencies and high frequencies from. That is all you need to know about trigonometry. I'm not sure why they make that a prerequisite class. And now that we know trig, this is sampling in one slide. So you might have noticed that in the tutorial description, we talked about digital signal processing. And it's digital because we're doing it with computers. Now, sound waves and most signals in nature in the real world are continuous. That means they have infinite resolution, they're all smooth and everything, but to get them into our computer so we can work with them in numbers, we have to do something called sampling, where we take them from a continuous signal into being a discrete signal. And the sampling frequency is how frequently we sample the signal. So this one, just the little blue lines are just showing these are the points I'm capturing, and so you end up with a kind of jaggedy signal. The higher sampling frequency, the more little blue points you have, and the higher resolution your digital signal is going to be. The lower the sampling frequency, the less resolution you're going to have, and probably the worse it's going to sound. And that is, those two slides are all